Hello, this is Dave May, and this is my final presentation for CSCI E92, the operating system on the Kineticus hardware running at 120 megahertz. One of the most important things I found was trying to get the memory settings correct. Um, that took a while. I thought I had it working early on, and then later I discovered as on the next problem set there was some flaws in it, so I spent more time. I think it's working fairly well. I used the first fit algorithm. Um, my malloc was used to allocate memory for the various functions on the operating system. It uses a split to divide the first free memory block. That's the largest to accommodate the malloc request, and it splits that, and the remaining portion is still free. I used my free to free the allocated memory from my malloc. That uses the merge function to combine the adjacent free memory blocks. And I also frequently use the memory map function, which maps out the size of the memory blocks, the address, and the status of the memory is either free or allocated. And I use that quite often to troubleshoot my malloc and my free functions. It has a lot of interrupts that were required to to build here and to use. There was a service handler interrupt, the SysTick timer interrupt, PendSV interrupt, the programmable delay block interrupt, the flex timer, and the serial port interrupt. I used a 15 as a priority as a recommended class in class value. That's the lowest priority for the SVC handler. I made the quantum interrupt a priority 14, which is the second lowest, and the so for both the SysTick and the PendSV. And I left the others basically as the defaults from Professor Frankel's files. Medium priority for programmable data block and flex timer and the serial port interrupt. I did manage to finally get multi-processing working with significant help from instructors and Professor Frankel. Um, so I created the multitask command to make sure that it worked. So it basically spawns the three processes that were required for the project. The first process allows users to enter characters on the Minicom terminals, what I'm using, and it displays there as well as on the LCD hardware. The second process displays a message switch 2 is depressed whenever the switch 2 is depressed, and the third is just flashes the LED based on the programmable delay block in a previous problem set. So they all run simultaneously, and I'll show you that. The multiprocessing stack was fairly complex. Took me quite a while to wrap my head around that, but what I did is I created a stack pointer with my malloc. I added the size of the stack and the as the starting address. So the first thing I push onto the stack is the SPSR value and at the highest address, and we go lower as the stack grows. So for each push, I decrement the by 4 bytes before pushing on the next word. Took a while and some help to get this working. The final project, I had to tame it down a little bit given the difficulty with multiprocessing. So what I'm calling this is a UART, a Morse code translation to LEDs with transmission speed control and combination lock security. So the user enters the command Morse code at the shell prompt. He's asked to to enter the proper combination of the touchpad. And when he does, he gets the proper combination lock. The next line comes up and says, asks him to start typing the characters for the Morse code translation. The Morse code can be the speed can be varied based on the using the digital potentiometer. Depending on your competency level, you can speed it up or slow it down, and get a good place where you can really interpret the dots and dashes. I created a few videos with my phone showing both the terminal and the LCD display and hardware. Several different videos, and I'm going to show you those. So the first one is the multitask. So the user types in multitask, and it asks him to start entering characters to the screen, and you can see they're echoed to both the terminal and the LCD. The orange LED, the third process, you can see it flashing, and so in the switch 2 is depressed, a message comes up. Start typing characters again. They're reflected on the screen. One more time, you can see the flashing. Push the switch again. The message comes up on the screen. Switch is depressed. And then we exit with Control D. The next video is the final project, the Morse code. So you hit Morse, and it's asking you to wait for the proper combination. And I've hit it the wrong one several times, but this one I got it right the first time. So now you start typing the code that you want to translate to Morse code, flashing LEDs, and you can see it's gone pretty fast right now. So you can slow it down, speed it up. I think I have a factor of about 5, so you can speed it up, slow it down by 5 times. So once all the characters are transmitted, it'll go back to the command prompt. So you can kind of see it's a little too slow, but at some point you can really dial it in, and I can tell exactly what a dash and a dot is. So the transmission's just about complete. That's just that one line, and it goes right, when it's done, it goes back to the shell. The final, we weren't required to create this, but given the memory file system, I created this to make sure to run a good test, to make sure what I was putting in the memory files was indeed what I was getting out when I looked at it again. So the first test, I typed David into a file, then I open another file, I type something into the next file, that's my wife, and then I read it back and I get exactly what it shows there. So that's pretty much the presentation. Yeah, it's been a bit of a challenge. It's been a lot of time, but I've learned a lot here. So thank you.